Now let's look at problem number 11. In this problem, we have a big triangle and also some small black and white triangles. The question is, what fraction of this triangle ABC is colored black? Okay, first of all, let's see. Clearly, this part equals 1/4. And then we have this part is 1/4 of 1/4, right? So this part is 1/4, 1/4, that's 1/16. And then if you look at each black triangle, small white triangle, so that's 1/16 and another 1/4, so that's 1/64. All right, what we get is if the each black one, so each black one equals 1/64. Then all we need to do is to find the number of these small black triangles. Clearly, we have 3 here, 3 here, 3 here, 3, 3, 3, 3, 3, 3. From here, we just derive the number of black triangles equals, that's 3 times 9, that's 27. Okay, so then we conclude fraction equals 27/64. Problem number 12. Which of the following numbers n has the property that 2n has more factors than 15n does? For this one, we need to memorize, recall how we calculate the number of factors for a given integer. Let's recall the formula. Say if I have m, I should put is m. This n, we first find its prime factorization. Say it's p1 times l1, p2 times l2, all the way to pk times lk. Here, each pi is a prime factor of this capital N, different prime factors of n. This L1, L2, Lk are just powers. And then the formula says the number of factors of n equals is L1 plus 1 times L2 plus 1 and all the way to Lk plus 1. So don't forget, when you implement this formula, don't forget you need to put a 1 here, so add 1 here. So this is how we calculate the number of factors. The formula is derived just by multiplication principle. Okay, now if we know the formula of a number of factors, we just check the numbers from A, B, C, D, E, and we can quickly identify the valid one is D. Let's check that. Here I have the n equals 3 100 times 5 100, okay? And then 2n will be 2 times 3 100 times 5 100. Then we apply the formula, the number of factors. So we get the number of factors equals, here the power of 2 is just simply 1. So it's equals, it's 1 plus 1 times 100 plus 1 times 101 plus what? So 100, sorry, it's 100 plus 1, 100 plus 1, and 100 plus 1, right? So that's 2 times 101 and 101. We don't have to calculate out. Now let's look at 15n. 15n is 3 times 5 times 3 times 100 and 5 100. This is 3 to the 101 times 5 to the 101. Again, we apply the formula of number of factors. This tells us number of factors equals, it's 101 plus 1 times 101 plus 1. That is 102 times 102. Now, clearly, 2 times 101, 101, if you compare these two, 102 times 102, the above is bigger than the one that's below it. So D is the valid number that 2 times n has more factors than 15 times n. Number 13. Here we have a soccer ball that consists of black pentagons and white hexagons. Now each each black pentagon is adjacent to 5 hexagons, right? 1, 2, 3, 4, 5. And then each white hexagon is adjacent to 3 hexagons, right? So that's 1, 2, 3, right? 1, 2, 3, sorry, right here. 1, 2, 3. So that's what I have, right? 1, 2, 3. Okay, so the question now, if we know then there are 12 black pentagons, the question is, what is the number of white hexagons? We have seen similar problems in past AMC8. The essentially is the same, but just in different contexts. There was a past AMC8 problem says in elementary school, there's some number of students and some number of teachers and some number of courses. Right? Each the student takes a certain number of courses, and each courses has how many students, and each teacher also teaches how many courses, like that. So that's basically it's a similar version. You can consider students, teachers, and also the courses as here we have the black and the white, right? Okay, now one way to solve the problem, what I like to do is we say, okay, so here we have those blacks, right? Black, it says we have 12 blacks. And then we have those white pentagon. Okay, white hexagon. All right, now here what we have is now let's connect line segment. If one black is adjacent to one white, we just draw a line segment. Because each black is adjacent to 5 white ones. Right? So if I draw the line, it's going to have 5 come out. 1, 2, 3, 5, right? Each one is 5 out. If I look from the perspective of the white ones, because each white one is going to receive 3 line segments. That's because each white one is adjacent to 3 black pentagons. So it's going to receive from here, I say 3, right? 3. Okay. Therefore, if I want to calculate, I say I want to calculate the total number of line segments. I have 2 ways to calculate. Either I just calculate from the perspective of black ones, right? If I look at this one, I will say each black sends out 5 line segments. So that's 12 times 5 equals 12 times 5. But also I can calculate from the perspective of the white ones, since each white one receives 3 line segments. So it's as if X is the number of white hexagons, right? Then this one equals 3 times X, right? Okay, so they should equal. From here, I quickly get the X is 20. Problem number 14. Here we have a triangle ABC. It's a right triangle. The right angle is on C. CB is 3, this is 4, and this is 5. Now we roll the triangle ABC clockwise along this horizontal line L. And then this is the second position, this is first position, and second position, third position. Clearly, after the third position, it's just going to repeat itself, right? This is just going to repeat, everything's going to repeat, right? Okay, and then we have that. All right, if we count from, let's say we start from here to count the pattern. That's because we labeled start from P1. You can start from the first one, it's okay, but I think it's more convenient since here we have the labels for P. So I think it's more convenient to count from the second one. Now you all the way you go to, this is start of P1, P2, P3, and all the way to 40. Since each pattern has 3, right? So 3, so this is 3, and then another 3. We just need to look at the remainder, 140 divided by 3. Right? We say, okay, 40 equals 3 times 13 plus the 1. The remainder is 1, so that means the 41 is going to be this one. So this is the 41. So it's 3, 4, and 5. Okay, right, because the remainder is 1. All right, so now we can calculate, and here there are, in total, we have up to that, it's 3 times 13. And each cycle, let's see, what is the length, right? We have, here's 5, here's 3, and 4. So each cycle is 5 plus 3 by 4. That is exactly 12, right? Okay, so it's a 12. Okay, so then we have the total length, which is just the length of from here C, right, from C all the way to right here. We have is 12. 12 times there are 13, right? 13 patterns. And then we have to plus this extra 5 right here, plus 5. But don't forget, we also have the first one since we count from here, right? So we count from here. So do not forget, we also have 3 here. So I need to put 3 back to here. So it's plus 3. Now, if we calculate this one out, 12 times this, so that's 36, 12. So 100, 156. So this is 156. And then plus 8, it's 164. Number 15, the problem says, in United States and in United Kingdom, the way people record dates are different. In United States, usually what people do is go with month, day, and a year. And in United Kingdom, the typical way is day first, then month, and the year. So the point is sometimes you can get confused. Like if you see a date, say you travel to England, that you get confused, like which is which. So this actually happened to me several years ago. I went to Britain. When I look at the expiration date on my visa, at first I thought my visa expired, but then I realized this is actually it's a British format. Okay. All right. Now the question is, we just need to figure out in how many days in 2020 that will not get confused for these two formats of recording dates. There are 2 ways to do. One way is you go direct. You just find out all those dates that will not get confused. For example, January 13. Well, even you put 13 in front of it, 13 cannot be a month, so that must be a date, right? So those things will not get confused. Another way is we go indirect. We first find the dates that could get confused, and then we subtract that from the total number of days in 2020, that's 360. The later one is probably more convenient, so I will go with the indirect approach. So solution. I will go with indirect method. Okay, so the total number of days. So first of all, the total number of days in 2020, because it's divisible by 4. So we know the total date is 366, not 365. Okay, and then we find the number of days that could get confused. This is easier to calculate. That's because if I look at the date, the time when it will get confused is only if both of them are less than 12, both of them are less than 12. Then you will get it might not be convenient to figure out which one is the month and which one is date, right? So that's the dates that will get confused. So you get is 12 times 12, which is 144. But among those dates, there are a certain number of days that is different. That's when the month and date are the same, right? If you have, say, June 6th or 7th of July, although it's less than 12, but because they are the same. So under the US format and the UK format, they're the same. You're not getting confused. So we have to subtract those exceptions, right? How many do we have? Of course, it's 12, right? So it's minus 12. We get is 132. So there are 132 days that you will not get confused. All right, therefore, so the answer is the number of days that will not get confused equals, you just minus subject, right? 366 equals 366 minus 132. So that's 234. Now let's look at problem 16. Here we have a parallelogram ABCD. We know this angle is 70. And then because this AD and BC are parallel, we may get this one is also 70. Since the AE bisects the angle BAD, so this one is also 70. This tells us this is 40, and this one is 140 because it's parallelogram. Okay, now I have this one is 25, and this implies the one we want to find is a 40 minus 25, which is 15 degree, right? Here we just use the fact within a triangle, the sum of three angles is 180. Number 17. Here we have a sequence A1, A2, A3. We know the first number is 3, and then the recurrence relation, that is from AM to the AM plus 1, is given by the following rule. If it's even number, then it's just divide by 2, the next one. If it's odd number, the next one is 3 times plus 1. Okay. The question is, what we need to figure out is what is a 20/20. Now, for this type of problems in AMC8, usually what you need to do is just plug the numbers into the formula and try to identify the pattern, because it's clearly this is not an arithmetic sequence or it's a geometric sequence, and those kind of sequences we are familiar with. What you need to do is do the calculations and find the pattern. Let's do it. Solution. Okay, we have the A1 equals 3. That is odd. And then by the rule, if it's odd, just multiply 3 plus 1. I just get A2 is 3 times 3 plus 1, which is 10. And 10 is even. And then we say, okay, if it's even, divide by 2. Okay. And then we have the A3 is 10 divided by 2, which is 5. That's odd again. If it's odd, multiply by 3 plus 1. Okay. And this gives us a 4. 3 times 5 plus 1, that is 16. This is again even. If it's even, divide by 2. Right? Accordingly, a 5 equals 16 divided by 2, which is 8. 8 is even again. And then we keep dividing by 2. A 6 is 8 divided by 2, which is 4. That is also even. And then we divide by 2. A 7, that's 4 divided by 2, which is 2. That's again, it's even. And then we have a 8. It's a 2 divided by 1. That is 2 divided by 2. That is 1. This is odd, right? And now we, because it's odd, we can do it again from here. I have a 9 is 3 times 1 plus 1, and this is 4. You see, we get 4 again, which is even, right? By this pattern, you say, all right, I'm going to get a 2 and 1 and then 4, 2 and 1. It's just going to repeat itself. So the pattern is after a 6, what is 4 to 1, 4 to 1, and 4 to 1. Okay, what do we want? We want to find a 20, 20. Now, go from a 6 to a 20, 20. How many do we have? We have 15 numbers. We just need to find the remainder, right? 2015 divided by 3, the remainder. We don't really have to do the calculation. Remember, we just need to add a shortcut. We just need to add the numbers together. So this is the 8 modular 3. So that's 2 plus 1 plus 5. Okay, so this one we know is 2 modular 3. So the remainder is 2 when divided by 3. And then we look at if the remainder is 2, here the pattern is 4 to 1 and 4 to 1, and this tells us we should just get the middle one because the remainder is 2. All right. Okay, then we get the 2. For this one, I want to make a remark. This problem is a special case of a very famous unsolved problem in number theory that's called Collatz conjecture. Sometimes it's also called 3n plus 1 conjecture. 3n plus 1, it just comes from here. Okay, the conjecture says, regardless what is the an, a1 is any positive integer. If you follow the sequence, eventually you can always, after finite steps, after finite steps, according to this rule, you'll see the pattern. You'll get to 4 to 1, 4 to 1, and 4 to 1. This is what it says. Or the conjecture says eventually you're just going to get 1. Right? If it's 1, the next one just be 4 to 1, 4 to 1. So this is the famous Collatz conjecture. Let me repeat. It says you can start from any positive integer, and then you follow this procedure. And after a while, well, how long depends. Sometimes, like for here, we just after 1, 2, 3, 4, 5. After 5, you see 4 to 1. If you just focus on 1, you have 1, 2, 3, 4, 5, 6, 7, 8, right? And the 8th one, you just get a 1. Now, for other numbers, you might take more steps. But the point is, regardless what is the first starting number, after finitely many steps, you will see 1, or equivalently, you will see 1, 4, 2, or 4, 2, 1, 4, 2, 1, this pattern. And this is the Collatz conjecture. It's one of the most famous unsolved problems in number theory. So far, people have used computer to check the validity of this conjecture for really large number. It's correct, but still, the proof people haven't been able to find the proof. Problem number 18. The problem says, due to the approaching fire, Ethan has to evacuate from home. He leaves at 4 p.m. and drives to his friend's house at 3 miles per hour. He plans to get there at 5 p.m. This immediately tells us the distance between Ethan's home and his friend's home is 30 miles, because 30 miles per hour and it's 1 hour. So we immediately get the total distance from here. This is 30 miles. Okay. All right, so let's keep reading the problem. After Ethan has driven for 4 miles, so this is 4 miles, he realized that he forgot to bring his laptop. So he drives back at faster speed, that's 40 miles per hour. All right, let's figure out that how many minutes Ethan has spent on his way. On this way, for 4 miles, because it's 30 miles per hour, so it's 4 divided by 30 times 60, right? So we get it's 8 minutes right here. So this is 8 minutes. When he drives back, because it's 40 miles per hour, it's 4 divided by 40 times 60. We get a 6 minutes, right? All right, so that means in total, he has spent 6 plus 8, which is 14 on the way. But also, the problem says it takes him extra when he comes back. It takes an extra 6 minutes before he could drive back. Right? Maybe he needs some time to find the laptop, and also probably needs to explain to a policeman that why he drives back, right? Okay, but anyway, so in total he spent 6, 6, and 8. That's 6 plus 6 plus 8, which is 20 minutes before he could drive back to his friend's house. Therefore, if we redraw the picture, when he start again, this is already 4:20 p.m. Right? So Ethan and his friend's home. Still, he wants to get there at 5 p.m. Total is 30 mile, right? 30 mile again. That does not change. 30 miles. Okay, then how fast he needs to drive? We just the speed. Then the speed. We get the speed equals here it's 40 minutes, so 30 mile divided by 40 minutes, right? From 20 to 5 p.m. is 40 minutes, and because it's miles per hour, so we should multiply by 60. Then we get is 100 divided by 4. That is 45 miles per hour. So that's the speed that Ethan needs to drive in order to finish the 30 miles in 40 minutes. Right. Now let's look at problem 19. The problem says John wants to make the largest cube out of this 6 times 4 times 2 rectangular wood. Of course, he has different ways to cut that. And the question is, what is the largest possible surface area of the remaining part? Right? We want to find that way of cutting this cube. Let's see, what are those different ways to cut this cube? One way, of course, you can just cut at the corner. This is one way. Or you can choose cut near the boundary, so near the face, and but not touch it to other side. For example, right? You can do things like this. This is another way to cut it. Right? Or you can cut right in the middle, like kind of just cut through the middle. And that's, you can do this, right? So we have 3 different ways to cut this cube. We can put this, so this is number 1, this is number 2, and this is number 3. When you look at the 3 different ways, it's kind of clear. This one is going to give you the largest surface area of the remaining part. Now, the reason is simple, because if you cut by this, we lose 2 surfaces, right? Let me put, if I put this small cube out, then we lose 2 surfaces, these 2. But meanwhile, we gain all the surfaces around the boundary, right? We say, okay, we just get all those things around the boundary. Therefore, if I calculate, but the other 2, we lose these 2, and also we lose at least one of those walls. And this one is we are going, but the third one will keep all those 4 walls. All right, okay. So we got this one is the largest. Let's just calculate the area. So the surface area equals the original one. So that's 6 times 4 plus 6 times 2 plus 4 times 2 times 2, right? So this is the surface area of the original rectangle wood. But as I said, we lose 2, and then you add 4, so we gain 2 more, right? Gain 2 more, and the plus this is 2 times 2 and times 2 copies, right? Lose 2, get a 4, so we get a 2. Okay, all right. So then here we have, this is 24 plus 2 plus 8, and multiply by 2, and then this is 8, okay? And here what we get is 44, so it's 8 plus 8. The final answer is 96. Problem number 20. Problem number 20 says we have a regular pentagon that is inscribed in a circle. We randomly choose 3 vertices. The question is, what is the probability that the center is contained in the interior of the triangle? Right. So let's calculate the probability. So probability, when the formula is a fraction, is the number of those valid cases, and then divided by the number of total cases, right? The number of total cases, it's simple, since we have 5 vertices, we choose 3 out. This is 5, choose 3, which will calculate. It's 5, which is the same as 5, choose 2. But okay, let's calculate anyway. So it's 1 times 2 times 3. That cancel, they cancel 2. We get this one is 10, right? Okay, so the total number of cases is 10. That's the total number of combinations. Now let's find the valid cases. Okay. If I choose, say one side, right? I fix one side, right? Regardless how you choose one side, and then we choose the third point, right? Third point. How many different ways we can choose? Clearly, the only way I can go is I can only do this. Therefore, it's clear you just fix one side, and the other point is just the opposite one, right? And from here, we get the number of good cases. So this is 1. And then if you do the other, 2, 3, 5, right? I have 5 good cases. So it's 5 over 10. That is 1 over